Hello. In the previous lecture, we were discussing about the Green's function, and today also we are going to continue with the same discussion, and we'll see some different other strategies in order to construct the Green's function. And yesterday we did two cases. One case was a homogeneous case. Another case we looked for inhomogeneous case. Mostly in physics, you'll find that Green's function would be invoked mostly for inhomogeneous cases, but I have done for both of them in the previous lecture. Like in the lecture one, we introduced it and we did it for a homogeneous case, and then we did it for an inhomogeneous case. And in inhomogeneous case, in order to find the Green's function, we saw that there were several properties. There were four properties which we had to satisfy. Apart from that, when you had this inhomogeneous case, your source function, that is your f of x, that is your inhomogeneous function, or sometimes called as forcing function, is replaced by a Dirac-Delta function, concentrated at, let's say, for tomorrow's sake, it was zeta. So all those things we have done. Okay. Today, again, we are going to continue with a few problems, and let us try to understand using problems the construction of Green's function. Okay. Okay. So let us try to construct a Green function for an oscillatory problem. Okay. For an oscillatory differential equation. So as you know that your simple harmonic oscillations are governed by an equation given by d square by upon dx square plus k square y equal to 0. And the initial conditions given to you are y0 is equals to 0 and y1 is equal to 0. Okay. So as you're aware, this is clearly a homogeneous differential equation. This is a homogeneous differential equation. In order to construct the Green function, the first thing is you know that your Green's function would satisfy the differential equation itself. Okay, so it will satisfy the differential equation itself. So given that, I know that my d square g upon dx square plus k square g can be written as 0. And given this differential equation, we know that the solution will be a form of some linear combinations of sines and cosines. So I would write my g x comma zeta either be equals to some a sine x plus b cosine of x, kx. So I'd write a cos kx plus b sine kx, and let's say your x lies between zeta and a. And if your x lies between, and here your a is 0 and your b is 1. So you can assess that using your initial conditions. Okay. The first thing is that your Green's function satisfies the differential equation since it is the homogeneous case. If it was an inhomogeneous case, then the function should be replaced by a function which is concentrated at a single point, that is given by a Dirac-Delta function. Okay. So this is a homogeneous case. Yesterday I took this particular case at first. So that is why I'm doing it first. Okay. Now, the second condition is your G must also satisfy the initial homogeneous boundary conditions. So homogeneous boundary conditions are given as G0 and G1 comma zeta should be equal to 0. So both of them are given. So instead of y, now you have G, and at x equal to 0, so your G at x equal to 0 should be 0 and G at x equal to 1 should be 0, which will give you that your A must be equal to 0 if you take this particular thing. And if you take this particular equation, then it will be C cos k plus D sin k must be equal to 0. So these are like terms. I would write it as 1. This will be your equation number 2. This will be equation number 3. Okay. And I will insist on that for examination. Probably you can just check these conditions. Probably selecting, rejecting among options would help you. instead of finding the entire solution, it may help you. I don't know, like if there's a multiple choice exam, and if you have 4 options, you just check whether the given Green's function is following your all these properties or not. If at all you can do some selection and rejection, it will ease your life. Now, it implies what? It implies that your, sorry, I will not write. It implies what? It implies that your gx comma zeta can be written as, because since a is 0, it can be written as b sine kx. Okay. So here I'll write x lies between zeta and 0, and your x lies between zeta and 1. Okay. So if I can write my d, d I can write as minus, you can say, I will write d is equal to minus c cosine k divided by sine k. So if I use this particular property, if I use this particular value and replace it here, what I will get? I will simply get c sine k cos kx minus c cos k into sine kx. Okay. And if you use this particular property, what you will get? You will simply get this to be equal to c sine k minus kx. So it is equal to writing this. So it will be, I think, I can write it as, if I take this, I mean, if I take k common out, so it will be equivalent to writing it is 1 minus x. Now this question to minus c sine of k minus 1 x, and then you have some division by sine k. So overall, this seems to be the Green's function. Now still you need to find b and c. So where your b and c can be found, you have 2 extra conditions which will help you out to find the b and c. The 2 extra conditions. The first condition is that your gx comma zeta must be a continuous function. So it must be a continuous function. So if it is a continuous function, then it should be continuous everywhere. And if it is continuous everywhere on 0, 1, then it should be also continuous at zeta, because there itself your definition is changing. Otherwise, you know that your sine kx is a continuous function. This is also a continuous function, hardly matters. Only continuity needs to be checked at zeta. So I am checking my continuity at zeta minus and zeta plus. So here I would do something like I will check the continuity. And if I check my continuity, what will I get? I will get b sine k zeta is equals to minus c sine k minus 1 zeta. And then you have something divided by sine k. And probably if I solve it up, so I will get what? I will simply get that my b is equals to, again, I can express my b as minus c sine k minus 1 zeta divided by sine k, and then you have some sine k zeta. So this is where we reduced ourselves to, right? So we have come to a ground zero that, okay, I've done something wrong. I think instead of x only, we write x now. So this is, I think, k minus kx only. So if I take k common out, so I'll, sorry. If I take k common out, so I will get x minus 1, sorry. So if I take x minus 1 here, so it will be, I think, there is a mistake here, I think. It will be zeta minus 1, and then there should be x. There should be k. Okay, is that clear? Okay, so I hope it is clear. Now, I'm not wrong. Zeta minus 1 will come out as k. Okay, I hope this is clear. Okay, you can also take this negative inside. All those things can be done. Okay, so overall, I know that my b is this. So I will write my gx comma zeta all over again, and that will be equals to what? It is equal to c. So instead of b, you just write c. So expression, it will be like sine of zeta minus 1 k divided by sine k into sine k zeta, and then you have this, that is sine kx. Your x lies between zeta and 0. And if your x lies between zeta and 1, then you have, again, something like in C only you have, थोड़ा सा difficult होगा, but कोई बात नहीं, minus c sine x minus 1 into k divided by sine k. So is that, I think it's done. I think it is like till now, I think everything has been done. Now the other condition would imply, what does that imply? It implies that your gx, that is the first order derivative with respect to x, and first order derivative with respect to x at zeta minus and at zeta plus, if I just subtract them up, there should be a jump discontinuity, and that will be equals to 1 upon minus 1 p naught zeta, where p naught is the coefficient of the highest order derivative. So highest order derivative for an oscillatory equation, if I'm giving it, is 1. So it will be minus p naught 1. Okay, so it will be minus p naught. And if I just find these differential derivatives, what I'll get? I'll simply get the derivative of this. This derivative will be equals to what? This will be equals to the derivative of I should take it here in negative, but I'll write it as 1 minus x. But at least my life becomes somewhat simple. However, it will not become simple because in any case, this negative would remain. Okay. Okay. So even if I differentiate it, I would get c, I would get cos, I would get 1 minus xk, and the derivative of 1 minus kx would be, I think, minus k. So I'll write minus k here. And there would be a sine k, obviously. And I can write here, your x should be equals to zeta plus. Then minus the derivative to the left of this. So to the left of this, all of these are constants, so forget about it. You have this derivative as k cos k x divided by, you have sine k, and then you have sine k zeta, and then you have minus c. So I'll write minus c here, and then I will write sine of zeta minus 1k. And all of this thing is equals to minus. I mean, this and this is at x equal to zeta minus. Is that clear? Now, if I just use all these things, I think what will I get? I will get minus kc cos 1 minus zeta k divided by sine k. And then this minus minus becomes plus. So it will become k cos k zeta c sine zeta minus 1 k divided by sine k and sine k zeta. I hope it is clear. If everything is fine in that case, so it will be equals to minus. Have I made some mistake? Just see if there is a mistake somewhere. So I should write the LCM to be sine k and sine k zeta, and here you will have some sine k zeta, and forget about this particular thing. Like kc, you just take common out. So kc taken common out, it will be minus sine k zeta, and then you have cos of 1 minus zeta k, and then you have plus cos k zeta, and then you have, I think, if I write it in again minus, so I'll take a negative again common out. So overall it will be negative, and this will be sine 1 minus zeta k. And this entire thing is equals to minus 1. So this minus becomes plus overall. Is that clear? So your overall, if I just talk about, so it will be like kc, and the numerator part is sine k zeta cos 1 minus k zeta, sorry, k zeta and 1 minus zeta k. So it will be sine k zeta plus 1, that is k, minus k zeta. So this is like sine a plus b formula. So this will become sine k zeta. I think again there would be zeta. Is there some zeta somewhere? No. Have I made a mistake again? Just see यार इसको कैसे करें. चलो, I think sine k है. And then you have, I think, नीचे भी 1 sine k remains, and then sine k zeta also remains. So 2b, this is 1. So it implies that my c must be equal to, if this gets cancelled, then it is like sine k zeta divided by k. So your c comes out as sine k zeta upon k. And using this c, you can write your Green's function eventually. So you just replace this value of c here, and you will get the appropriate Green's function. Is that clear to you? Is that clear to you? I mean, till now everything is clear. Is that clear to you? Okay. Now let us see that can we construct Green's function forever? Like, for ऐसा हो सकता है, can it happen that there may be we cannot have Green function for certain boundary value problem? So is that a possibility? But if that is a possibility, what are the conditions required for existence of the Green's function? Let us think about it. So I'll give you a problem. Let us take a problem of dy upon dx3 equals to 0. And given the boundary condition y0 equal to y1 equal to 0, and this is like y dash 0 plus y. If I'm not wrong, this will be y dash 1 equal to 0. So if these are the given conditions, let us try to construct a Green's function for the same. So let us try to construct a Green's function for the same. So if I try to construct a Green's function, as I know, this will be equal to d3 g upon dx3 equal to 0, and that implies that your g as a function of x comma zeta would be some quadratic function, and that would be, let's say, ax square plus bx plus c for all x lying between zeta and 0, and for all x lying between zeta and 1, it will be some dx square plus ex plus f, where a, b, c, d, f और ये सारे जो हैं, I will require these conditions to find the relation between ABCs. So if I just use the condition, first condition that is at x equal g at x equal to 0, your g must be equal to 0. What it will yield me? It will yield me that my c is equal to 0. Is that clear? And if I say my g at 1 comma zeta is 0, that implies my d plus e plus f must be equal to 0. So there are two conditions till now. So I have come up to two conditions. Now, further, the other condition says that my y dash 0 and y dash 1 should be 0. Y dash 0 plus y dash 1 should be 0. So if I just differentiate it, so it will come out as 2ax plus b. Just give me a minute. Battery is so from conditions I will get 2ax, the derivative, plus b. This will be like b, and then you have some at x equal to 0, and then you have the derivative here, 2dx plus e at x equal to 0, but at x equal to 1, sorry, this should be equal to 0. So it implies your e plus 2d plus e must be equal to 0. So you have third condition in this form. That is, your b plus 2d plus e must be equal to 0. Now, if I just take another condition, that is a continuity condition at zeta. So at continuity condition at zeta would require me to write this. So that implies, I think that implies a zeta square plus b zeta, and b is already 0, c is already 0. So should I write it? Should I not write it? I will not write it. Even if I write it, I know my c is 0 after all, so it hardly matters. And this should be equal to what? This should be equal to d zeta square e zeta plus f. Okay. So eventually I will get what? I will get simply a minus d zeta square b minus e zeta, and then there would be some minus f, given that my c is 0. So I'm doing it. Okay. Is that clear? And the last condition that we can use is the derivative being discontinuous at zeta. Am I audible right now?
नहीं भैया
अभी आ रही है? Am I audible? Am I not audible?
Yes, sir. Audible.
Okay. Because there is a power cut now. So okay. So if my gx is like if I say that it is non-differentiable at like zeta, so there would be some some discontinuity that is equals to, I think, minus 1 upon p naught. So it is like minus 1. I hope till now everything is clear. Okay. Okay. Now you just try to find the values of A, B, C's and all those stuff. So when given this particular differential equation, so the derivative, if you see, the derivative would come amount to writing 2A. I think this will be like zeta, because you see the derivative to the right would be AX, sorry, this would be
2D.
Zeta plus, I think, E zeta, and then it should be plus F and minus, I think it will be 2A zeta. I think it will not be A here. This will be 0, I think. So I think you just find this, like plus, I think there was some E here, no, B here. Is that clear? This should be equal to minus 1. So I am giving you just a minute because I need to change some settings. Meanwhile, you just find these values of A, B, C, D, E, F. Okay, I'll join in the lecture, don't worry. Just give me 5 minutes. Okay, just find A, B, C, D's, E, F's, and you will get something that is important. Okay, I'm giving you around 5 minutes just to find that up.